So, today we will start the topic of integral dependence. So, let A be contained in a ring B, an element x in B is said to be integral over A if there exists A1 up to An in A such that x power n plus A1 x power n minus 1 plus a n minus 1 x plus a n to 0. A and B are rings. So, one says B is an extension of ring A. Okay. So, this is a concept that comes in. If A, so this is, by this notation I mean A and B are rings, and when I say A contained in B, it means A is a subring of B, okay, as the operations being the same. Okay. So, that is the I mean the notation means that. So, this is a concept that comes in number theory as well as in algebraic geometry. Okay, it is a important concept that if you do a course in algebraic geometry, you will see relation between what is called the integral closure of a ring in number fields that keeps coming in number theory, and the integral closure property of certain rings with that has close relation with algebraic curve associated to or the ring which is associated to curve. The integral closedness of that ring has close association with the ring being smooth or not. Okay. The curve being smooth or not. We will see one example of such sometime, but you will see more such examples if you do a course in algebraic geometry next semester, or course in algebraic number theory and so on. So, let us look at some simple examples. One quick example is that if you look at k x square contained in k x, x is a variable, k is a field, okay, then so this is A, this is B, x in B is integral over A, right. It satisfies the equation y square minus x square, right. X will satisfy this equation, right. So, if I take n to be 1, n to be 2, and a1 to be 0 and a2 to be, this is 0, this is x square. So, this is integral over A. Let us look at another very interesting example. Okay. So, you must have seen in your algebra course that S3 acts on k x1 x2 x3. how does this S3 act on this ring? So sigma of xi is x sigma I. This is in general sigma acting on any p x1, x2, x3 is p x sigma 1, x sigma 2, x sigma 3. Okay. Then this is a group action. Now let me call this ring A, call this ring R. Okay. Look at this ring R S3. This is set of all p x1, x2, x3 in R such that sigma acting on p is same as p. Okay. Then what do you know about this ring? Do you well, this might not be known to you, but this one can easily show that this is equal to E1, E2, E3, where E1 is x1 plus x2 plus x3, E2 is x1, x2, x1, x3, x2, x3, and E3 is x1, x2, x3. Okay. What is this RS3? They are all symmetric polynomials. This elements of this are called symmetric polynomials. However you change xi to xj, they are unchanged. Okay. These E1, E2, E3 are called elementary symmetric polynomials. Okay. This equal to this, it is not very difficult to show. I will leave it to you as an exercise. This complete this. Okay. Now can you see that x1 is integral over, so let me call this A. Okay. And so now we have A contained in R. Okay. Can you tell me whether x1 is integral over, so I want to get a polynomial. So what is the idea? So when would you say that x1 is integral over A? If I can find a polynomial, let us say p y, such that you put y equal to x1, it is 0. Okay. Now if I look at this polynomial, consider the polynomial y minus x1 times y minus x2 times y minus x3. What is this polynomial? Y cube minus, what is the coefficient of y square? Y square times minus x3, then y square times minus x1 and y square minus y square times minus x2, which is E1 times y square. What is the coefficient of y? E2. E2 times y minus E3. Right. So therefore this, so py, I take py to be this, then p of x1 is 0. In fact, p of xi is 0 for all I from 1, I mean I equal to 1, 2, 3. Because it's, if you put x1 equal to y equal to x1 or x2 or x3, this is going to be 0, which means we have an integral equation for x1 over a, similarly for x2 and similarly for x3. Okay. So, this says that x1, x2, x3 are integral over a. So, what have we really done here? We have taken one x, one element, okay. We have taken one element and looked at all possible and the orbit of x1, right. So, we have taken an element from the polynomial ring, looked at y minus that element times y minus all the products, possible products, right. We are looking at y minus a, then y minus sigma a. So, or in other words, what we have done is we have looked at y minus sigma dot a sigma in S3. We did not take the entire product, but if I take any a in R, this will work, and every coefficient is going to be, each coefficient is going to be inside the ring A, right. What will be the so suppose this is this has to be of degree. If I take this polynomial, what will be its degree? How many elements in S3? 6. So, this will be of degree 6. We did not take this here, we sensibly took a smaller polynomial, but in general if I for any a in A, if I take this, this will have degree 6. What is coefficient of y power 5? It will be summation sigma dot a sigma in S3 minus of this, right. This polynomial will be y power 6 minus this one. Is this symmetric? These are all symmetric, right. If I apply, this is a polynomial, sigma dot a will again be a polynomial in R, but if I apply some tau, if I apply tau on this sigma a, this will be same as this one, right. Tau sigma acting on a, tau varies over S3, but that is same as this element itself. Therefore, this is fixed by all elements in S3, and hence this is in A. This will be sigma dot A sigma in S3. S3 is a finite group. You look at tau sigma where sigma varies over S3 is same as sigma varies over S3. Okay. So, therefore, this implies this element is in A. Similarly, look at coefficient of y power 4. We will have sigma 1a, sigma 2a and products like that. So, therefore, each of these coefficient will be in A, and hence this will give me a integral equation for A. Okay.
So that means the polynomial you differentiate
not really a special case, this is a smaller polynomial in fact, because if I take, for example, if I take the take sigma to be 2 3 and apply on x1, it will remain x1. So if I take this one, this will be square square square. See, if I take, so I take this y minus sigma x1 product sigma in S3, what would this be? This will be y minus 1 square y minus x2 square y minus x3 square, because this will, see what is this, I am looking at y minus sigma acting on x1. For sigma equal to identity acting on x1, there will be y minus x1. Sigma equal to 2 3 acting on x1 will again be x1. Now in this one, if I take 1 2 3, this will be x1 will be sigma of x1 will be x2, okay. And if I take, so yeah, the transposition 1 2, that will also give me x minus y minus x2. So there are two of them. Similarly here, so we will, this will be this one, okay. So in general you might not require whole of S3 to get a polynomial integral equation, but this is a safe one. If I take this, that is going to serve as a polynomial for the integral equation, okay. So now what we have done is, this is a very particular interesting case, but we can replicate this in a much more general situation. What is that? I take a ring, let R be a ring and G be a finite subgroups of automorphisms of R. I take a finite subgroup of automorphisms of R. Automorphisms are isomorphism from R to R, they are called automorphisms, okay. This is in particular, this is an automorphism, permutation of variables is an automorphism of kx1 x2 x3, okay. So we take a finite subgroup of automorphisms of R and look at A to be equal to Rg. Now can you tell me whether A is R is integral over A? I look at this A B in R. Can you tell me whether this is integral over A? Can you give me a polynomial which will serve as a, which will give us integral equation for A? Take Py to be we are doing exactly what we did there, not doing anything other than that. This is G is a finite group, okay. So this is a polynomial of degree equal to the cardinality of G. One of them is identity, so therefore PA is 0 and every coefficient of this polynomial will be fixed by, okay, this is this clear what this is, okay. Rg is set of all A in R such that G of A is yeah, g of a is a for every g in G. Now, if I take summation G A for a fixed A, summation G A, G varies over G is fixed by, if I apply G prime on that, G prime G as G varies over G is same as G varies over G, it will be the whole group again. So, therefore, every coefficient of this will be in R G. So, therefore, this will give me an integral equation for A. So, this says that every element of R is integral over R G. We will see more examples a little later. So, now suppose I have a ring extension A contained in B. Okay. I look at all elements in B which are integral over A. Okay. Can you give me some elements from that set? So, let C be set of all x in B such that x is integral over A. Can you tell me some elements of C? All elements in A will be in C, right? Then C is, and A is contained in C. So, this is a C is containing A and contained in B. Naturally, one tends to ask if C has some additional structure. Is it a submodule? Is it a subring? Is it an ideal? What is it? Okay. Does it have some structure, nice structure compared to the structures of A and B? Okay. So, this is obtained by observing some equivalent conditions for the integrality. Okay. So, let B rings A contained in B be rings, then the following are equivalent: x in B is integral over A, Ax is a finitely generated A module, there exists a finitely generated A module C containing A and X. There exists a faithful A module, faithful Ax module M, which is generated by n elements finitely generated over A. What is faithful module? So, an A module M is faithful if annihilator of M is 0. There are no elements that kills M. Okay. So, let us prove this. One implies 2. If x is integral over a, then suppose x is integral over a. Then x power n, there exists a1 up to an in a such that x power n plus a1 x power n minus 1 plus an is 0. Can you tell me an A module generating set for Ax now? 1x up to x power n minus 1. So, this will imply that. So, there are many ways of saying this. This implies that x power n is equal to minus a1 x power n minus 1 minus an, and that implies that Ax is generated by one x x power n minus 1 as an A module. Any higher power you can substitute x power n, this for x power n and reduce to an equation of degree n minus 1. Okay. So, that proves the second statement. Now, 2 implies 3. I am given that Ax is a finitely generated A module, and here I have to prove that there exists a finitely generated A module C containing A and x. Just take C to be equal to Ax. And 3 implies 4. I know this and I want to prove that there exists. Okay, so I should probably here write instead of which is finitely generated. I do not really, since I am not really talking about elements here, in fact one can state this as Ax is generated by 1 x x square up to x power n minus 1, and this generated by n elements, and here also generate. So, that n, if I mean I can add in these 3 or I can just omit in 3. 3 implies 4. Again I can take m to be equal to c. Why would it be faithful? Take m to be equal to c. Now, see, the A module C is containing A. So, if I have some y, if y times C is 0, C contains A, which means C contains 1, which means y times 1 is 0, which is y is 0. So, now let us look at 4 implies 1. What we are given is a module M, which is a faithful Ax module and which is finitely generated as an A module. Okay. We need to prove that this x is integral over A. Okay. Or in other words, I need to produce an integral equation of the form x power n plus a1 x power n minus 1, so on and so forth. Okay. So, therefore, let us look at consider the map phi from M to M defined by phi of M equal to x. This is the multiplication map. Now, yeah.
There exists x belongs to V or for all x belongs to V?
No, this is for the fixed x. X in B is integral implies a x. So, all these x are same, x here, x here, x here, x here, all of them are same x. If for an element x in B, if that is integral, then this is true. If for an x in B, if Ax is a finitely generated A module, then the third statement is true. Similarly, if there exists a C containing A and X, then this is true. Similarly, if I have a Ax module with this property, then X is integral over A. That is what we are trying to prove. So, the X here is fixed. The X here, 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 all are the same. Now, phi is an endomorphism of M. Okay. Phi of M is contained in M, obviously. Okay. Now, what I do is I just apply the Cayley-Hamilton theorem, which what does it say? There exists. So, here okay, let me write it clearly. Suppose M is generated by M1 up to Mn, okay. Then I can write this phi delta ij minus, see each x mi is an element of M, and hence I can write it as a finite linear combination of finite a linear combination of M1 up to Mn generated by over A. What we are given is that M is a finitely generated over A. So, if this is, I can write this Aij acting on this M1 up to Mn, this is 0, right. So, I take, this is my matrix, let us say, if I call this matrix X, and if I take X prime be the cofactor matrix with cofactors of X, then what do we have? X acting on this matrix on this vector M1 up to Mn, this is 0. We are just going through the Cayley-Hamilton theorem in some sense, but this is determinant of this matrix X times In acting on M1 up to Mn. Now, we need to use that the module is faithful over Ax more generally. See, this will be a polynomial, some phi power n, right. This is a polynomial in phi. Determinant x will be some phi power n minus some I will just write now as a1 phi power n minus 1 plus a n minus 1 phi plus a n, this acting on, so this is the determinant, therefore phi power n plus a 1 phi power n minus 1 a n minus 1 phi plus a n acting on any mi is 0 for all I from 1 to n. But what is phi power n acting on mi? Phi is an A module homomorphism. It will be x power n mi. So, this implies that x power n plus a1 x power n minus 1 plus etc. a1 a n minus 1 x plus a n acting on mi is 0 for all I from 1 to n. Or in other words, this element is in the annihilator of M because it annihilates all mi's. So, this implies x power n plus a1 x power n minus 1 plus etc. a n, this belongs to annihilator of M, but since annihilator this is an element in Ax and M is a faithful Ax module, this is 0. So, that implies x power n plus, and that implies that x is integral over A. Is the proof clear? What is 0? So, okay, I am writing phi m1, this is x m1. Whatever this be, I am just writing it as summation aij a1j mj, j from 1 to n. Similarly, for each I, mi is this, and these are these coefficients. This is the same matrix that we considered while proving Cayley-Hamilton theorem, or the lemma before Nakayama lemma. Okay. So, the matrix is same as that. We were just, see, from here I could have directly come to this one, because by directly applying the determinantic lemma, but I just went through the proof completely, that is all. Okay. So, there are some nice corollaries, one of which is the question that we started with. So, first we observe something, that if b1 up to bn in B are integral over A, then A b1 up to bn is a finitely generated A module. Because A b1 will be a finitely generated A module by the proposition. Now, A b1 b2 will be a finitely generated module over A b1, but A b1 is a finitely generated module over A. So, if you take the corresponding generating sets and look at all the products, that will be an A generating set for A b1 b2, okay, and keep going on like this. So, therefore, this is a finitely generated A module. Write down a proof for this. Okay. So, if you have, so this is more generally true, that if A is contained in B, contained in C, they are all rings, and if B is a finitely generated A module and C is a finitely generated B module, then C is a finitely generated A module. Just take, if this B1 up to n is a generating set for B, and C1 up to Cm is a B generating set for C, then Bicj is an A generating set for C. So, this is using this result one can prove that this is a finitely generated A module. Suppose C is set of all x in B such that x is integral over A, then C is a subring of B containing A. So, here if I know that x is integral over A and y is integral over A, how do I know x plus y is integral over A, right? I mean, from the integral equations of x and y, I cannot possibly get a integral equation for x plus y, right? They will be entirely different. So, therefore, we use the result that we proved. Okay. See, here to prove that it is a subring, we only need to prove that it is closed under addition and multiplication. Once they are there, then all other properties are associativity, distributivity, etc., they are all part of ring, B itself. So, therefore, we do not need to worry about them, we only need to prove that this is closed under addition and multiplication. So, if I take x in x comma y in C integral, so they are integral over A, so yeah. So, this implies that A x comma y is a finitely generated A module. This and x plus y comma x y belongs to this one by the third property that we proved in the last proposition. If there exists a finitely generated A module containing x, then x is integral over A. So, here I have a finitely generated A module containing x plus y as well as x y. Therefore, x plus y and x y are integral over A. So, that proves that it is a subring. So, the collection of all integral elements of B over A is a subring. So, this let A contained in B be rings, the set the subring C equal to set of all x in B such that x is integral over A is called the integral closure of A in B. Okay. If B is equal to if C is equal to B, then we say B is integral over A. Okay. C is equal to A, then we say that A is integrally closed in B. and if A is a domain, if A is an integral domain, then the integral closure of A, see here the terminology is integral closure of A in a super ring, but if A is a integral domain, then we say that the integral closure of A, the integral closure of A is a notion that represents the integral closure of A in its fraction field. So, if A is an integral domain, then the integral closure of A is the integral closure of A in its fraction field. Okay. What is the integral closure of